Okay, so it looks like we're getting the hang of the reaction stuff. Just in taking a quick glance at some of those quizzes while you guys were handing them in, okay, it looks like most of the mistakes were not about understanding how the reactions work, but more about messing up a formula or a name, okay, or something like that. Okay, little mistakes like that, but those are the things we have to make sure we do well, okay, because really the reactions part is the easy part. Okay, as long as we get the little fundamentals that build it up, right, we're good on each one of them. All right, so what we're going to look at today is how to predict the products of a reaction, which really isn't any different than what you've been doing. You already know how to recognize a reaction type, and that's really all you have to do in order to be able to predict the products of a chemical reaction. Okay? It's not like you're pulling it out of thin air. There's a pattern that each reaction follows, and all you have to do is follow that pattern. So if we look at this example right here, right? So I'll have you guys write this one down as a predicting example. Okay? I'll give you a minute to get that down on paper. So the first step in predicting the products of a chemical reaction is to write out the reactants in formula form. Okay? Most of the time those will be given to you, but on the odd occasion, like let's say your unit exam or an assignment, you might get the reactants in words, and then you'd have to write them out in formula form. Right? But you can't really start the predicting process until you have the reactants in formula form. Once I see those two things there, I can start to analyze what's going on. What I see there as reactants are two ionic compounds. I see beryllium iodide and chromium-3 bromide. If I have a reaction that starts out with two ionic compounds, what kind of reaction am I looking at? Double replacement, yeah. Okay. So if I can recognize that it's a double replacement reaction, all I have to know then is what happens in a double replacement reaction. According to my notes, what happens in a double replacement reaction is very simply that the metals switch partners. Okay, so all I have to do on the other side is write that instead of being with iodine, beryllium is going to be with bromine, and chromium is going to be with iodine. Okay, so now I know who's with who. I'm not done yet though, because these are both ionic compounds and I've done nothing with them except decide who goes with who. What do I have to do with both of those? Like, are these compounds written correctly? I've just paired them correctly. I haven't written them correctly. Okay, I have to do what with this compound? Drop and swap. Yeah, I've got to make sure that the compound is written correctly. So bromium's a -1, beryllium is a +2, so I'll be looking at Be, Br2, of course. And then for this one here, okay, I know that iodine is a -1, and I know from this side that chromium was the +3 variety. Okay, so I'm going to go over here and say, okay, it's a +3 and drop and swap. So I'll have Cri3. All right, now my reaction is written correctly, but now the reaction needs to be what? Balanced, because it isn't yet. So biggest number is 3. It's on both bromine and iodine. Okay, and they're both a -1 charge, so it doesn't matter which one I do first. I'm just going to do iodine because it's first. Okay, I've got 2 iodine over here. I've got 3 of them over there. How do I balance 2 and 3? I heard somebody whispering. You were right. You said common multiple. So what's the lowest common multiple? 6. Okay, so what do I have to multiply 2 by to get 6? 3. Okay, so I put a 3 here, right? And then what do I put here? A 2. Now that I do that, I've got 2 chromium. So I've got to go back over here, okay, and put a 2 in front of the chromium. When I do that, that gives me 6 bromines. I need to go over here and put a 3 there. Well, lo and behold, balancing those bromines gave me the right number of berylliums on both sides too, and now I'm done. Predicting reactions always follows this pattern. Okay? Write the reactants, identify the type, allow the type's pattern to tell you what the products will be, drop and swap, balance the reaction. Or drop and swap and check for special elements if you have a reaction that produces special elements, and then balance. Okay, everybody with me there? So you do have to know your reaction types, and you have to know the pattern for each one. Luckily, there's only 5, and they're all pretty straightforward. Right? That's all you have to do with predicting. You already know how to balance reactions. That's nothing new to you. Okay? The only thing that's new here is having to actually use the patterns you know to figure out what will be on the other side. Okay? So let's try a couple here and see how we do. All right, I want you guys to try those 2 reactions there. I'll give you a few minutes on those. All right, so for our first one here, I've got an element reacting with another element. What kind of reaction starts that way? Synthesis reaction. Okay, in a synthesis reaction, those 2 elements are going to do what? Combine. Yeah, according to Dalton, atoms can combine in simple whole number ratios to form compounds. So, since one of them is a metal, magnesium, I'm going to list it first, and the other is a non-metal. Okay, so I'm going to list it second, and then I'm going to drop and swap this thing. This is a -1, this is a +2, MgI2. Okay, well, that wasn't too hard. Okay. And that reaction's already balanced now. Okay. Did I still follow the same rules I said a minute ago? Yeah. Okay. Did I say, all right, identify the type, use the pattern to predict the products, drop and swap, balance the reaction? Okay, follow the same steps. I didn't have any special elements. Okay, well, iodine, but it was already told to me. Okay, and I just went from there. All right, second one. I have an element reacting with an ionic compound. What reaction type is that? Single replacement. Okay. According to the pattern for a single replacement, the element that's by itself replaces the part of the ionic compound that it is like. Since chlorine is a non-metal, that means it's going to replace the non-metal in this ionic compound, which is fluorine. So that means that on this side, fluorine is going to wind up alone, and sodium is going to end up with chlorine. Okay, so I figured out the pairs using the pattern, but I need to check for 2 things.
Does the order matter if we put chlorine second? Like,
You mean like you went ClNa?
no, like NaCl plus F.
Absolutely makes no difference.
Okay.
Yeah, I could write F second or NaCl, doesn't matter. Yeah. Okay. So I have to still check that this is swapped and dropped correctly. It is, all right, so that's good. And what else do I need to check for? I have to check for molecular or special elements. Do I have any? Yeah, fluorine. Little things to check for, okay? Single replacement are the ones that have the most things to check. Right? You're gonna likely produce a special element. You're definitely gonna produce an ionic compound that needs to be dropped and swapped. All right, now that I've done that, all that's left is to balance the reaction. On this side there are 2 chlorines, and on this side there's only 1, so I need to put a 2 there. Right? When I put the 2 there, I'm going to need a 2 here, which also balances my fluorines, and now the reaction is balanced. It really isn't much different than what you were doing already. Okay? It just requires you to know the patterns for the reaction types that we've gone over. Okay, try those 2. All right, what kind of reaction are we looking at number 3? Combustion reaction. Okay, got carbon and hydrogen reacting with oxygen. These ones are actually a little easier for predicting because it doesn't matter what there is in terms of the number of carbons and hydrogens. The products are always the same. What are the same two products of every combustion reaction? CO2 and water, always the same. It's just how much is going to change, right? So CO2 and water, right? Those are always the products of a combustion reaction. We just know those, okay? Now that I've got those, I don't have to drop and swap anything because they're all molecular. Now I just have to balance, okay? Do I need both balancing rules here? Yeah, because an even number of carbons. All right, so I'm going to start with a 2, okay? 2 times 2 is 4 carbons, so I'll put a 4 there. 2 times 6 is 12 hydrogens. 6 times 2 is 12 hydrogens. And now I can balance the oxygens last. 4 times 2 is 8, plus 6 more is 14. 7 times 2 is 14. Okay? Everybody all right with that? Okay, so predicting combustion reactions is probably the easiest one because there's not really any predicting to do. We just memorize the products. Yeah. All right, and then for number 4, decomposition reactions. Now, decomposition reactions are the easiest to predict, but people mess up in the products by forgetting to check for what? Special elements. And decomposition reactions almost always produce at least one special element. Right, so in the case of this one here, okay, we've got disulfur trioxide, and it's going to break down into sulfur and oxygen, both of which are special. Okay, S8 and O2. Now I've got to balance this thing. Start with the biggest number. Okay, that's the easiest way to go. There's 8 on that side. Now there are 8 on this side, but that gives me 12 oxygens, so I'm going to need a 6 there. And now it's balanced. Okay, are we kind of seeing how these work? Right? Really, we taught you the fundamentals already. You know how to write reactions, you know how to balance reactions, and you know the types. Okay, now that you know those things, now you can apply what you know to something else. All right, I'm going to put a few more up here. I want you to try, and then we'll go through them together. Okay, so try those 3. If you're having trouble, let me know. Okay, let's look at the first one here, guys. So what kind of reaction have we got if we start out with those 2 ionic compounds? Double replacement reaction. Okay, in a double replacement reaction, all we do is swap the metals so that they have different partners. So that means then that beryllium is going to end up with oxygen, and sodium is going to end up with phosphorus. Okay, so now I've figured out who the partners are, but I have 2 ionic compounds that have not been dropped and swapped, so that's the next step. This is a +2, this is a -2, so that compound is fine the way it's written. Okay, and then I've got this one that is a +1 and this one that is a -3, so I'm going to have Na3P for that. Right, now they're dropped and swapped correctly. My last step is to balance that reaction. Right, so biggest number is 3 and it's on beryllium. So we'll put a 3 here, but you know what, that's not going to work when we do it. I'll show you why here. If I put a 3 here, then I've got to go over here and put a 3 in front of the sodium. That gives me an odd number of, it gives me a different number here. Oh no, sorry, we'll be able to make it work. Sorry, I misread it. Okay, it gives me 6 sodiums, so I'm going to go over here and make sure I have 6 sodiums. Putting that 2 there takes care of my phosphorus. Sorry, I was thinking I had a 3 on it. Okay, so now the reaction should be completely balanced. Okay, all right, does this get a little trickier if I give you the reactants in words only? Yeah, because then you got to get the reactants right as well in order to get the products right. Okay, so it does add kind of an extra layer onto that. Okay, so I'll leave you with, I'm just going to move this one up so you can see it. Okay, I'll leave you with those 3, okay? And we'll go over those in a few minutes here. Okay, anybody want more time on those three? Oh, I've been recording that whole time. Nice. There'll be a big silent gap in there. Okay. So for number 6, okay, I've got an element reacting with an ionic compound. What kind of reaction am I looking at there? Single replacement reaction, okay? So in a single replacement reaction, the lone element replaces the part of the ionic compound that it is like. Since magnesium is a metal, that means it's going to swap out for lithium. So lithium is going to wind up alone, okay? And magnesium is going to end up with nitrogen. Okay, did I produce any special elements? Lithium's not special, okay? And then I've got a drop and swap magnesium nitride. All right, this is a -3, this is a +2, so when I drop and swap, I'm gonna get Mg3N2, okay? So I got two things that are a 3. Magnesium's the bigger charge, so I'm gonna try it first. Okay, I'm gonna put a 3 there. I'm gonna balance my nitrogens with a 2 here and a 6 here. Ought to do it. Okay, questions on that one? All right, what kind of reaction am I looking at in number 7? Okay, number 7 is a decomp, yeah. Okay, it's a single compound, that's my only reactant, so the only reaction that starts that way is decomposition. That means that it's gonna break up into its 2 elements. Okay, what do I need to know about those 2? When phosphorus is by itself, it comes as a 4. Okay, and chlorine has a 2. All right, 4 is the biggest number, so we'll balance it first. Put a 2 there to balance the 4 phosphorus. That gives me 6 chlorines. A 3 there will balance my 6 chlorines, and that reaction should be good after that. Okay, the biggest thing with decomp reactions is getting the right number on any special elements that are produced. Okay, and then for number 8, okay, what kind of reaction is that? Combustion, okay? Products of combustion are always the same 2 things, CO2 and water. And now I gotta balance it. I don't have an even number, so I can just balance alphabetically. 7 carbons, 16 hydrogens, 8 times 2 is 16. 7 times 2 is 14 oxygens, plus 8 more is 22. 11 times 2 is 22. Okay. How are we feeling about this? Okay, so this is what we're going to be working on the rest of today. Most or part of tomorrow. Any part of tomorrow we'll also be doing the pre-lab for our reactions lab, which we're going to do on Thursday. The pre-lab is going to involve us doing some predicting of the reactions that we're going to have happen in our reactions lab. All right, so by then we have to be reasonably good at this so that we can predict those reactions and write them properly. Okay, oh, that's physics. Why is that on there? Those are both questions. Okay, so what I would like you guys to try here, I'm just going to put a couple more up on the board here. And I'll have you guys work on those. So let's say, And then one in words, because we haven't done one like that yet. Okay, guys, let's have a look at these ones. So on number 9, what kind of reaction am I looking at? Synthesis reaction. I've got 2 elements, okay? When they go together, what kind of compound are they going to make? Ionic or molecular? Ionic. So which one of them do I write first? Sodium. Okay, so this is a trick that I play basically every semester. I'll put this one on a quiz, something like this, where I'll list the non-metal first and catch people because they'll go, oh, it's a synthesis reaction, and they'll go like this. And forget that the metal has to be written first in an ionic compound. Okay, you'd be surprised how many people I catch with a simple trick like that. Okay, so it's going to make sodium chloride. Okay, that's a -1, that's a +1, so that's dropped and swapped correctly, but I've got to balance it. There's 2 chlorines over there, so a 2 and a 2 will make that balance. Okay, just a little trick to watch for. Okay, it's just me seeing if you remember how to write ionic compounds. All right, for number 10, I've got an element reacting with an ionic compound, in this case, lead 2 chloride. How do I know it's the lead 2 and not the lead 4? Well, I look at the compound. Chlorine is a -1 and there are 2 of them. That means there's 2 negative charges, so this is the lead with the 2+ charge. That's important because on the other side of this reaction, lead is going to swap out, okay, and be with phosphorus. And chlorine is going to wind up by itself. And it's a special element, so I put a 2 beside it. Right? Now I've got to drop and swap this compound. This is where figuring out that lead was the 2+ is important, because I've got to drop and swap it on this side. Okay, we're going to have Pb3, P2. Okay, so important to watch for those little things. Okay, it's important. Now, I've got to balance this reaction. 4 is my biggest number, so I'm going to put a 2 here to balance my phosphorus, because that's a 2. Okay, when I do that, it gives me 6 leads. So I got to put a 6 here. That gives me 12 chlorines, so a 6 there will take care of that, and I will have 1, 6, 2, 6 for my balancing. Okay, questions on that one? Okay, now, just in walking around, I put a little trick in number 11, and I got people with it. Just in walking around, I can see a few people who missed something in number 11. Okay, copper 2 hydroxide. What does the Roman numeral tell me about copper? Its charge, 2+. It is with hydroxide, which is a -1. What needs to go around this? Right. If you don't put brackets around this and you write out the whole reaction, is it balanced correctly? Because you have 1 oxygen and 2 hydrogens, unless you put brackets around it. You'd be surprised how often people forget that. Okay? And I don't know what it is about hydroxide. They don't forget it with carbonate. They don't forget it with nitrate. But hydroxide, man, people forget brackets for that thing. Because it doesn't have a number. Right? There's no little number here that people are like, oh, right, I got to put another bracket there. And they just write a 2 without it. Okay? It's not right if you just write the 2. Okay? Reacts with potassium permanganate. That's KMnO4. It's a double replacement reaction, so the metals will swap. Okay? Copper will end up with permanganate, MnO4. Okay? And potassium will end up with hydroxide. That's dropped and swapped correctly. No brackets required. This one needs brackets. A 2. Okay, and then we got to balance the whole reaction. So permanganate needs a 2. Okay, that needs a 2. That fixes that, and we're done. Okay, it's a little trickier if I give it to you in words, and that's what we'll work on tomorrow. Okay, taking them in words. Okay, good job today, guys.